and brings over 26 years of experience in teaching, research, and industry. His research focuses on physical layer issues in wireless communications, applications of AI in 5G and 6G communications, and RIS assisted wireless communication NOMA for next generation communications. He has published more than 150 papers in high peer reviewed journals and conferences, holds 3 patents, and has successfully completed several government and non industry sponsored projects. Professor Kumar's contributions have been recognized with awards such as Best Paper Award at IEEE Globecom 2023 and IEEE IC MOCE 2023. He has guided many PhD, MTech, and BTech students and currently supervised. So he's also a visiting researcher at the NTU Singapore and Nanyang Technological University. He serves as a consultant to Tejas Networks Bangalore, Rakuten Mobile Japan, and Simovus USA. So welcome, sir. So kindly share the screen and start your presentation. Please, sir.
Hello, am I audible?
Yes, sir, you are audible, sir. Perfectly audible, sir.
Okay. So, good afternoon. Sorry for this delay in this connection of WebEx. Well, I hope participants are able to hear me, right? Okay. So today we are going to discuss about the 5G. What are the challenges, and if there are challenges, then what are the enabling technologies which make 5G a success? Because 5G has been rolled out in most part of the country as well as across the globe, and in India it has got a very good coverage. So we'll see that when we move to 6G or 5G advanced, understanding of 5G is very important. So I will just go through that and see how much you are able to. And my session will be interactive, right? So these are my slides. So brief introduction, then I will discuss about LTE, 4G, then requirements for 5G, challenges, what are challenges and what are the facilitators. And we'll talk about dual track, evolution and new RAT. RAT means radio access technology, and then some R&D technology areas where you may be interested to research. New waveforms, millimeter wave, massive MIMO, HETnets, cognitive radio, D2D communication, and final conclusion. Right? So I think this slide number 3 is visible. Okay. I hope it is visible. So if you see the slide, and I'm talking about data rate on the x-axis and mobility and coverage on the y-axis, and you may see that we have indoor users and outdoor users, and then we are seeing a linear red curve which talks about the spectral efficiency, and we see that when we are moving from 1G to 4G, the spectral efficiency is increasing linearly. So what I mean to say that when you move for the higher generation, there is a requirement of transmitting more bits per hertz, right? More bits per second per hertz, right? So that we are able to achieve in 4G, up to 4G. Even 5G, it was a challenge, but we are able to achieve that. Then we talked about 2 types of switching. One is circuit switching, other is packet switching. So circuit switching was primarily used in 1G and 2G, although it was for some time it was used in 2.5G and 3G also, where circuit switching means that we have end-to-end connection, and the dedicated channel, the dedicated resource is available end-to-end. There is no shared channel. But from 3G onwards, we switch to packet switching, where we are talking about packets And here we are using the IP network. We don't have any dedicated resource. The resources are shared. Right, then you talked about license spectrum. So most of this 1G to 4G and 5G, they are all using license spectrum. But there are services, luckily Wi-Fi and Bluetooth, they are using unlicensed spectrum. That's why they are very popular and they're available everywhere. So when you discuss about evolution from 1G to 4G, because to understand the challenge in 5G, first you have to understand how we have evolved from 1G to 4G. So what we have observed that when we talk about an evolution, but from 1G to 4G, each generation, uh, each generation supports higher mobility, better coverage, higher data rate, higher quality of service, right? So moving from one generation to other generation means that you are adding more value to your network. So, and just now we have discussed that 1G and 2G are they are circuit switching, and when you talk about 2.5G to 3G, they are using a hybrid mode. Means that both they use circuit and packet switching, but 3.5G to 5G they are invariably packet switching. So what I am trying to emphasize is that nowadays everything is as a packet communication. Even if when you are talking over a phone using 4G, it is packet communication. So they are using IP networks, and so most of this 1G to 5G they are using licensed spectrum, but there are some services which uses unlicensed spectrum. That's why they are very popular. So just one slide on 2G and 2G. If you observe that it has two generations, 2G and 2.5G. And standard wise, GSM, you all are aware that in India we are following GSM. And in some countries we followed IS-95, that is CDMA. And you can observe that we can only support 10 kilobits per second. So this is very interesting to understand that for voice communication, 10 kilobits per second is good enough. But for internet browsing and surfing the net and all, we need higher speed, and that was possible with GPRS and Edge. These are two techniques. They are still used in practice. And GPRS supports 50 kilobits per second, and Edge supports 200 kilobits per second. But that is very slow. This data rates only supports some browsing of the net, opening the emails and all. But that it takes a lot of time because uh, uh, the speed what they support is very less. So at the end of 1990s, we observed that we need higher speed. What was offered by 2G was not sufficient, so we thought of going for the higher speed. And here comes the third generation 3G standards, which started in the early 2000. And just you observe that in 3G, you observe that 3G also has two generations, 3G and 3.5G. And 3G has two standards. And you observe the data rate they are supporting. This is 384 kilobits per second, right? So this is quite a high data rate compared to 2G, where we're supporting 10 kilobits per second. Even when we use GPRS and S, it was 50 kilobits, 100 kilobits. But now we are supporting 384 kilobits per second. So, and here what we are using, then 2G we used TDMA technology, but here now we are using wideband technology that's called CDMA, and this is here wideband technology because a total of 5 megahertz of bandwidths are available, right? So 5 megahertz is termed, anything above 5 megahertz is termed as a wideband wireless technologies. So 3G supported this wideband technology. And if you go to this 3.5G, you observe that we can get a speed of 5 to 30 megabits per second. And that was a radical change from low speed of a few kilobits per second to 5 to 30 megabits per second. Now you may ask that, sir, what is so important with this 3.5G, where we are using this HSDPA, HSUPA, or e-video technologies, which supports 5 to 30 megabits per second. So just for understanding that, if we all are using 3G phone now we are using 4G, but with 3G phone also from 2010 onwards, we are able to do video conferencing and video calling. The biggest revolution was the 3.5 generation, 3.5G was that we are able to do video calling and video conferencing. The reason is that for video calling and video conferencing, we need minimum 10 megabits per second per stream over the air. So in 3G, it was not possible, but in 3.5G, it was possible because we are able to support more than 10 megabits per second, and then we are able to get this video calling and video conferencing. That was the biggest advantage of going from 3G to 3.5G. Now coming to this 4G, which was prevalent from 2010 onwards. So 1990s was the era of 2G. From 2000 to 2010, the era was for 3G and 3.5G, but 2010 onwards till 2020, early 2020, we have this 4G. And 4G, we observe that it has three standards: LTE, WiMAX, LTE Advanced. And you can observe the data rates has increased significantly. Now, with LTE, you can support 100 to 200 megabits per second. WiMAX can support 100 megabits per second, and LTE Advanced can support greater than 1 gigabits per second. Now, how it is possible, right? From 384 kilobits per second in 3G to 5 to 30 megabits per second in 3.5G. Now in 4G, we are able to get 100 megabits per second. That is a 3 to 5 times increase in the data rate over the wireless channel. How it is possible? So there are two techniques which are instrumental in implementing 4G, or I can say that there are two techniques which were instrumental in supporting this 100 megabits per second over the air, and these two technologies are orthogonal frequency division multiplexing, that is OFDM, and multiple input, multiple output antenna system, MIMO systems. So anybody, if you are a graduate, if you are a researcher, if you are a faculty, understanding of OFDM, orthogonal frequency division multiplexing, and multiple input, multiple output techniques are very, very important, because these are two techniques which make 4G a very popular standard. Still, we are using 4G widely, right? In India, 4G is still very popular everywhere, not in India. Everywhere, 4G is very popular. And these two technologies made it possible. And even when you go to 5G, or even 5G, even when you talk about 6G also, this OFDM and MIMO is going to exist, right? So these two technologies were possible, were responsible for giving us this 100 megabits per second data rate over the air. So this is summary. Just in one slide, I have kept that when you talk about generation 2G to 2.5G, then 3G to 3.5G, then 4G. What we discussed, that the data rate supported from 2G to 2.75G is 10 to 100 kilobits per second. That was primarily used for voice and low rate data. But when we moved to 3 to 3.5G, the data rate supported was 300 kilobits to 30 megabits per second. And that, in addition to voice and data, we have video calling and video conferencing in 3.5G. 4G, we are able to get a data rate of 100 to 200 megabits per second. And here we are able to get online gaming and high definition TV. So you see, 3.5G was good enough. But if we talk about high definition TV now, using your mobile handset, you can easily stream high definition video, right? And for that, we need 100 megabits per second, because high definition TV video transmission requires multiple streams of 10 megabits per second, right? So one of the biggest advantage of 4G was that we are able to have high definition TV over the mobile devices, and the speed has increased tremendously. So the download speed of any from any website, any document, or any data, or quality of video conferencing, video calling has increased tremendously in 4G compared to 3.5G. So now, briefly, I will discuss few of the important areas of 4G, because that is the basis of 5G. So 4G, like I told you that in 2004, November 2004, we felt that although early 2000 was the where 3G was becoming popular, but at the end of 2004, we realized that we need advanced generation, advanced technology, which can support higher performance. This should be backward compatible, means that if you are using a 4G phone, it should be able to give you 3G services also if 4G is not available, wide application. So 4G is basically a 4G and LTE, they are same. They are used interchangeably. 4G. So LTE is basically next generation mobile broadband technology and promises a data transfer rates of 100 megabits per second. And they are based on UMTS 3G technology. And the last point is very important, that it is optimized for all IP traffic. All IP traffic means that we are using TCP IP protocol for transfer of video, data, text, image, and voice. Everything is over the IP network. Any doubt? Any question up to this point? Any question? Okay, let's move further. So this is slide about this OFDM, which is basically the foundation for LTE and Wi-Fi. And your understanding of this is very important, because I have just kept one slide because uh, this OFDM is the basis for 5G also, and that's the basis for 6G also, right? So if you see in OFDM, we have data which we have serial data. So first we do is coding and modulations. I hope that you are familiar with that, coding and modulation, and then we do serial to parallel conversion. Then what we are doing is that we are using IFFT, inverse fast Fourier transform. This IFFT is used because we need orthogonal subcarriers. You see here in the bottom that in CDMA we are using a single carrier, right? But in OFDM, because single carrier transmission with higher data rate is subjected to frequency self-read channel. Or in other words, if you use 3G and if you transmit 100 megabits per second or 50 megabits per second using the CDMA technology, your data, your received signal will be distorted and you will not be able to recover your transmitted signal. And you require a very complicated equalizer. But in OFDM, what we are doing, in place of a single carrier, what we are doing, we are using multiple subcarriers. And each subcarrier will carry your information. But the condition is that these subcarriers should be orthogonal. Meaning by that, orthogonal means that they should not interfere. If you see this diagram at the bottom, there are multiple subcarriers, each subcarrier carrying independent information bits. They all are transmitted simultaneously, but whenever any subcarrier is at the maximum value, other subcarrier has zero value. It means that although they are overlapping, they are not interfering. This is a very, very important concept of OFDM. They allow overlapping, but they don't allow interfering, because whenever any subcarrier has a maximum value, the other subcarriers have zero value, right? And generally we sample at the peak value of any subcarrier. So IFT was used, inverse fast Fourier transfer, to generate orthogonal subcarriers. Then we are using cyclic prefix. Why we are using cyclic prefix? Because it takes care of orthogonality in multipath channel. Multipath channel orthogonality is lost, but with cyclic prefix, we can able to restore back our orthogonality, right? Then we do windowing infantry. Windowing infantry is very important because this takes care of out of band emission, because we whatever we are transmitting, we want that it should be within the same bandwidth what is given to our transmission, and then finally it is sent to RF section, right? Is it clear? Any question from the audience? Because understanding of DM is very, very important. Okay, let's move further. So what are the advantage of OFDM? So OFDM, if you have seen that, because although we other subcarriers are overlapping, they are not interfering. So in same bandwidth, we can transmit multiple transmission, multiple bits. So it is especially efficient. They are robust in multipath environment. They can coexist with current and future systems. And because we are using multiple small subcarriers which occupy small bandwidth, right? So your subcarriers are subjected to less frequency selective, or you can say that frequency selective channels are converted to frequency flat channel. So even if there are some interference or distortion, we can design a simple equalizer. But there are disadvantage. Disadvantage is that they are very high. They're sensitive to the interchannel interference. They are sensitive to frequency, clock, and phase offset. Any offset, whether it's a frequency, clock, and phase, that will result in loss of orthogonality. That is the biggest challenge in OFDM. And another challenge is that they are subjected to very large peak to average power ratio. What happens that because multiple subcarriers are being added up. So when they are added up, it is possibility that peak signal power increases. It is maximum compared to the average power, and that drives your RF amplifier into the nonlinear region, and that will create a lot of distortion. So PAPR is a very critical issue, and a lot of research has been put how to take care of PAPR, how to reduce this effect of interference due to PAPR. If you find the applications, OFDM is everywhere. You see that in standards like 802.11 AGN, they are used for your LAN networks, that is wireless LAN and Wi-Fi. Then 802.16, that is Bluetooth, and 802.20. OFDM is even used for fixed and wireline transmission like the ADSL. ADSL, I don't know how many of you have heard about that, is asymmetrical distance subscriber lines. They are used over a twisted pair cable where we can use these cables to transmit our signals over using a broadband. Initially, this twisted pair cable are narrowband channels, but if you use OFDM, you can transmit at a very high data rate, and the same twisted pair cable which was not supporting a high data rate now can support a very high data rate using OFDM, and that technique is called ADSL. That's called asymmetric digital subscriber line. Now coming to the mobile and radio, it is everywhere. You talk about digital audio broadcasting, you talk about digital video broadcasting, that is DVB-T, then HyperLAN 2, WiMAX, physical layer architecture for 3GP, that's LTE and 4G. And for your understanding, recently we have a 3GPP meeting in Bangalore in August 2025, and OFDM has been suggested for 6G also. Even 6G, we are going to use cyclic prefix based OFDM. So you cannot afford not to understand OFDM. You understand OFDM very properly, because OFDM is the standard that is being used in the, 4G also, that are being used in 5G also, and that has been proposed in 6G also, right? So this is a very big gain for all of us, that if OFDM, which is is a tested technology which has been used in 4G for the last 4G is already there for the last 15-20 years, and we are using this OFDM, which is tested technology. That's why even when talk about 6G, we have decided that in the worldwide forum that OFDM will be going to use for 6G also, but definitely there will be some modification, and we can say that this modification will help us to cater the very ultra high speed requirement of 6G. Now coming to fifth generation 5G. If you see this 5G, it has a very typical challenge, right? Challenge wise that you see that we are talking, if you talk about 5G, we are talking about data rate of 1 to 10 gigabits per second. So the 4G, we are talking about 100 megabits to 200 megabits per second. But when it comes to 5G, the targeted data rate is 1 to 10 gigabits per second, right? So in addition to that, what we are targeting that in 5G, the traffic is going to increase. So these all are estimate what we felt at, around 2014. 2014 onwards, we started working on 5G. Because what we expected that from 2020 onwards, the data traffic is going to increase 10,000 times more. What is there was in 2014. Number of devices that is being added to the network will be 10 to 100 times. Latency, we are talking about 1 millisecond latency. That was unthinkable in 4G. Battery life, 10 years battery life, because most of this 5G technology are based on sensors, IoTs, low cost for machine to machine, 10 gigabits per second data rate when we're talking about fixed wireless access, then 100 megabits per second when we are talking about low end data applications. So 100 megabits per second, which was the maximum limit, what we got in 4G is basically for low end data rate application in 5G. So challenges are how to support 1 to 10 gigabits per second data rate in real network, 1 millisecond round trip latency, high bandwidth in unit area, enormous number of connected devices. How many? 10 to 100 times more devices. What is prevalent in 4G? And in 4G, we never claimed that we are going to offer 100% coverage. But in 5G, we talk about almost 100% coverage, anytime, anywhere connectivity. Anytime, anywhere. Anywhere means that even if it is a hilly terrain, if it is a desert, if it is mountain, everywhere your network should be there. But challenge is that we are talking about reduction in energy uses by 90%. So energy consumption, if it increases the carbon footprint, and that will pollute our ozone layer. So what we want that even we are talking about gigabits per second, but the energy consumption should be 90% less. 90% less energy consumption, but we want a data rate of in order of gigabits per second. So in average, what we are talking about is low power consumption. Now, just one challenge I will discuss, which is very critical because a lot of use cases in 5G they require ultra reliable low latency. So if we talk about so what we are doing from 4G to 5G, that the latency is being reduced from 10 millisecond to 1 millisecond latency, right? So it is almost 1/10 of the latency what is being provided in 4G networks. So in LTE, that is 4G, how we are getting 10 millisecond latency is that in your device, the mobile device, what you are using, the requirement, minimum requirement for your, processing of everything in mobile devices is 4 millisecond, right? And when you go to the tower, BTS tower, that requires minimum 4 millisecond. Then if you are in a core network, it will require 1 to 2 millisecond. But we talk about, so internet, if you are going outside, same country, then it's fine. It may go to outside also, that will add more latency. Considering that we are in the same network, so total latency will be 4 plus 4, 8 plus 2, 6, 2, 10. So 10 millisecond latency is required, right? Round trip latency means that when you are talking, your signal will go to the receiver and receiver will respond to your signal. It will come back to it. This is called round trip latency. So 10 millisecond latency is there in the 4G network what right now you are using. But 5G, what we need, what we have the challenge that from 10 millisecond, we have to come down to 1 millisecond. It means that everything inside this mobile device should be processed in less than 0.5 millisecond, and in the base station side, in the network side, it should be less than 0.5 millisecond. Now you can imagine that how difficult this is to have in practical systems. And for your information, till date, we have not come close to 1 millisecond, but we are around 3 to 4 millisecond, and which is good enough to support some of the use cases like remote surgery, like self-driving car and all, tactile internet and all, right? So we have some use cases we require very small round trip latency. Any doubt here? Okay, let's move further. Now, this is slide which speaks a lot, right? Where round we are in the year 2020 onwards, right? So although we are halfway through 2025, but this will give you that what is expected in the next 10 years, right? So next 10 years, what is expected? So one is the area where we are talking about enhanced mobile broadband. Now, enhanced mobile broadband means what? Whatever we have in 4G is fine. But in addition to that, what we want, very high data rate, high spectrum efficiency, high mobility, right? Low PPR in uplink and simplified vision design, high data. So this is what we are expecting in 2020 to 2030. Even if we have 5 years through, this you have to understand that we have not achieved everything what is required in enhanced mobile broadband. If you are going for high speed, like bullet trains or aeroplane, we are still facing difficulties. Although some of the airlines, they are able to give internet services, and that is because we are able to enhance our mobile broadband, right? Using the satellite network. So the second part, which is more critical, is that massive machine type communication. So in 5G, there is shift between the enhanced mobile broadband, which is now 30% of the traffic that is being carried by 5G networks. 70% is by devices, right? Machine to machine communication, massive machine type communication. And one of the vertical is IoT, Internet of Things. And then we are talking about ultra reliable low latency communication. So what is about IoT? What are the challenges in IoT? So you may be aware that we are talking about, high speed, sensor networks that is used for smart grid, smart cities, smart homes, right? This is very common words that is being used. So have this IoT, successful. The first condition that it is a non-orthogonal transmission. What OFDM, what we are using in 4G and enhanced mobile broadband, we cannot use here because IoT devices are basically asynchronous. So we have to take this condition of orthogonality, what we are using, that is parted away. So non-orthogonality, high spectral efficiency, low complexity, low PAPR, asynchronous transmission, minimum out of bandwidth. And these are the requirements for what? Smart grid, smart cities, smart homes, smart industry, industry 4.0, intelligent transport system. They all require these conditions, that there should be low complexity, minimum out of band radiation and all, right? Now, other critical application is ultra reliable and low latency communication. You may ask, sir, where we need this? So this is used for tactile radio, autonomous self-driving vehicles, driverless car. Other words is driverless car. there is no driver and the car is moving. So you have to give the intelligence to the autonomous vehicle which have the intelligence of a driver. So collision avoidance, traffic sense, cognition capability, everything you have to give. And for that, what the requirement? That requirement should be that the latency should be sub-millisecond. It should be immune to Doppler. Doppler means that whenever you are moving, there will be Doppler shift in the receive frequency. And that changes your reception frequency. What is transmitted and reception frequency are different and low complexity. So although we are halfway through, we are in 2025, we have achieved some significant advancement. And that's why that is called 5G advanced, where we have achieved something. But still, we are halfway through. A lot of things are still in research, perspective we are doing, and hopefully we'll achieve all the requirements of your 5G advanced network. So I'm making your understanding more clear, where we are talking about this 2020 to 2030 timeline. You observe very interesting things. The data rate increases 10 times every 5 years. This is a trend till date. So every 5 years, your data rate increases by 10 times. So in 2030, what you can expect? 1 terabits per second for Wi-Fi, right? You may feel that it is unrealistic, but that will be a requirement in 2030 after 5 years. Right now, we are talking about 1 gigabits per second for cellular network. In 2030, it will be 100 gigabits per second. Now, question is that how to tackle? These are some research problems which is very open. All the researchers, all the audience who are here, they have to understand that these are the problems which we have to tackle. Right? There are some advancement which has been made in the last 5 years, but that is only I can say that we have achieved 25 to 30%. Still 70% is remaining to be solved. Right? Now coming to this enhanced mobile broadband, what we are talking about is that the peak data rate will be 110 Gbps, then 100 Mbps for high mobility. If you are moving in the bullet train or high speed vehicles, 100 megabits per second, and traffic is increasing 10,000 times. Right? So these are challenges for enhanced mobile broadband. Then we are talking about machine type communication. What are the challenges? We know that in IoT that latency should be very less, power consumption should be less, the receiver should be the capacity of the receiver should be very less, right? Now, there are few applications already we have discussed: tactile internet, remote surgery, and all, self-driving cars. That is termed as ultra reliable and low latency communication. Now you may ask, sir, what do you mean by ultra reliable? Ultra reliable means that the reliability should be 99.99%. Because when you're going for remote surgery, you are going for driverless car, you couldn't afford to have even a 1% less reliability. It should be close to 100% reliability. And the latency should be 1 millisecond, less than 1 millisecond. These are challenges we are facing, right? And in 4G, we have taken advantage of all low-lying fruits. It means that all the technologies we have used. So same technologies we are using 5G also, we have advanced that. Not same technology, we have advanced that. But still we are not close to 1 millisecond. We are not close to 99.99% reliability. We are not close to 10 Gbps peak data rate. We are not close to 100 Mbps high mobility data rate. But we have done some significant contribution. So just example for tactile internet. Tactile internet, what happens that in 4G, we talked about content communications. Content are delivered like video, text, voice. But in 5G, we are steering and control communication. Everything like healthcare will be taken as one service that will be transmitted in one go. Traffic, sports, education, manufacturing. So up to 4G, what we are doing, communications to deliver content, video. But in 5G, we have to do steer and control, just steer and control virtual and real objects in 5G, right? And that is where we talk about that is it is augmented and real what AR and VR communication, right? So tactile internet talks about total, control of virtual and real objects. So how we move from 4G to 5G, because we know that 5G is a success. Although there are challenges in 5G, still they were facing some challenges, but we are able to implement 5G. So how we have implemented? So there are two paths. One path is called the evolution path. Evolution is that whatever we have developed for 4G, we are adding more advancement in these 4G technologies, and we are able to support some of the services, some of the requirements of 5G. The main point is that 5G has two frequency bands. One is sub 6 gigahertz, that is FR1, below 6 gigahertz, where we are mostly operating from 3.3 to 3.8 gigahertz. Here, what we are using that we have advancement from 4G. We have evolved 4G to 5G. That is called sub 6 gigahertz communication. And what we say that this communication is backward compatible. Backward compatible means that whatever we are able to support in 5G, if we are not able to support that services, we will get the 4G services. The 5G services, if not available, move to 4G. If 4Gs are not available, move to 3G. It means there will be no disruption. There should be no disconnection. We will be able to get services, but definitely there will be no disconnection. Right? But when you talk about this new RAT, radio access technology, that is millimeter wave communication, that is FR2 communication, there we are not putting this constraint that the system should be backward compatible. Probably it will not be backward compatible because millimeter wave is totally a paradigm shift. That's why we say it as a revolution. Evolution is fine, but millimeter wave communication or new radio access technology, that is a revolution. Paradigm shift. No constraint of backward compatibility. So, in short, in early 2020s, ITU, International Television Union, they finalized the vision for 5G. That's very, very interesting. So what it says that 5G includes support for explosive growth of data traffic. Explosive growth of data traffic, because data traffic is going to increase 10,000 times. Support for massive number of machine type communication, 10 to 100 times, millions of sensors, millions of devices, and support for mission critical and ultra reliable and low latency communication. The support for mission critical, right? There are some mission critical applications, defense applications, and ultra reliable and low latency communications. This was the vision with 5G was designed, and 5G is being implemented throughout the world. Right? What are the key technologies to implement this 5G? So first we'll discuss about the evolution path. Evolution path means that from 4G to 5G, sub 6 gigahertz, we have enhanced the technologies what is used in 4G so that we have enhanced data rate of more than 100 megabits per second. And we are able to add more devices and all. So one important technology is software-defined networking. SDN. So now what is happening in 4G is that if you have to add more services, new services, you have to change the hardware. But in 5G, it is not there. Utilizing the resources efficiently using software-defined networking to serve a large number of devices. So everything is software-defined based. So by changing this software or embedded systems, we will be able to add more users, new services and all. No need to replace the hardware. Then we talk about full dimensional MIMO. In 4G, you use MIMO. But in 5G, we are talking about FD, full dimensional MIMO. Means that it utilizes large of antennas placed in two-dimensional, that is 2D antennas. This another word is full dimensional MIMO is 2D antennas, where antenna array panel are can generate narrow beams in both the horizontal and vertical directions. We are keeping antenna in both horizontal and vertical direction, and they can generate narrow beams in both horizontal and vertical direction. So it will improve the system performance by realizing higher order multi-user multiplexing, because we have now antennas placed in both horizontal and vertical direction, and significantly improves beamforming and spatial user multiplexing. So beamforming is very critical because in dense environment where there are so many, like your railway station, like your stadium, where users are very closely packed. So your beam should be pointed. First, you have to localize the user. Where is your user located? And then you have to position your beam to that. Localization and position is becoming very critical in 5G now, right? So that will improve when you have good beam forming. Beam forming is important in 5G, and that we are able to achieve using 2D. And when I discuss about new RAT, we'll see that we are able to achieve using your massive MIMO. Then we are talking about license assisted access LA using LT. So here what we are doing, that we have an unlicensed spectrum. There are a lot of spectrum which is unlicensed, as well as there is spectrum in 2G, 3G, 4G which is unutilized, right? How to make this possible, that the spectrum, because the spectrum is a very scarce resource, very important resource. How to utilize these resources, unutilized spectrum? For that, what we are doing, that we are improving the utilization efficiency of unlicensed spectrum as well as licensed spectrum. Another word is called carrier aggregation. We are doing carrier aggregation, that multiple spectrum holes are there. So just try to use unutilized spectrum, whether it's a licensed band or unlicensed band, and combine them to provide higher data rate or to add more number of users. So three techniques we have discussed. Software-defined networking, that was not there in 4G, but that is used in 5G. Then we have used full FD two-dimension MIMO. Then we talked about carrier aggregation. Now we are talking about the fourth important technology, that is called non-orthogonal NOMA, non-orthogonal multiple access. Because this IoT, massive machine type communications, there we cannot have this orthogonal transmission, right? We have to restore to non-orthogonal transmission. Then only we will be able to support more number of devices. So NOMA is an important technique that is employed for IoT transmission. But only problem is that when you go for NOMA, there is a lot of interference. So we have to remove the interference. And one of the important techniques which is used to remove the interference in NOMA is successive interference cancellation at the receiver, right? We talk about grid communication because we cannot afford to have more carbon footprint, which will pollute our environment, which will have more ozone penetration layers, right? In addition to that, we talk about low power consumption and less carbon footprint to the nature. Power consumption requirements should be 90% less, and so it should support less carbon footprint. Carrier aggregation enhancement, just now we have discussed that machine type communication is very critical, because we are more in 5G, we are talking more about machine type communication rather than the enhanced mobile broadband. Then the last one is wireless security. Now, because you are using phone pay and this Google Pay and everything, and you are able to do transaction anywhere now. Digital transmission is very common, and you may see that in this case the security, this wireless security, because there may be security threat, cyber threat, cyber crime, digital arrest, a lot of things are coming up because your wireless transmission in 5G is vulnerable to eavesdrops, a lot of hackers and all. So one of the important area which is booming now, which is very important now for the success of 5G is the wireless security or cyber security or security of our digital networks. Now, coming to another part of 5G, that is the new radio technology, which is totally a new technology. That is a paradigm shift where we were talking about transmission in millimeter wave frequency band from 24 gigahertz to 28 gigahertz, right? So right now we are concentrating on 24 to 28 gigahertz, where the lambda, the wavelength of transmission is in terms of millimeter wave. Although we have very huge bandwidth, but design challenge is there, right? We'll see what are the challenges of going to this new radio access technology, that is the which is so 6G, beyond 6G, 6 gigahertz, it's fine. But when you talk about millimeter wave, 24 gigahertz and above, things becomes totally different, totally different. A lot of challenges, design challenges are there. So what are the key enabling technologies we are going for 5G in millimeter wave? If you see this diagram at the below side, that we are talking about 24 gigahertz and above, right? That is a wide frequency band we have considered from 24 gigahertz to 100 gigahertz, but we are considering right now on around 24 gigahertz, 25, 24, 28 gigahertz. This large millimeter wave bandwidth, right? Then below 6 gigahertz, we have advanced 4G, and we are trying to get 5G services. So there are techniques which are helping us to have this millimeter wave communication in 5G. That is massive MIMO, then head nets and small cells, device-to-device communication, and cloud RAN. This radio access network will be on cloud. This cloud technology has become very important and very critical nowadays, because we cannot have a separate or dedicated hardware or storage device or data centers for a specific company or a specific area. So what we have done everything on the cloud. It means that that will be shared basis, anybody can use, and that will make it very efficient, right? Otherwise, it is very difficult to provide computing requirements of shifting your communication processing at millimeter wave. So millimeter wave, definitely we know that it requires high frequency antenna elements are smaller. Why millimeter wave is good? Because now we can have a smaller devices, because more we move in high frequency, lesser with antenna size. So huge amount of spectrum available. Millimeter wave is good for spectrum. So you see that 28 gigahertz, 38 to 49 gigahertz, there's a lot of windows are there in millimeter wave which can be used. So improve performance in dense crowd, because now when we are millimeter wave, your beams are very narrow. It can be pencil beam like laser beams and all, and you can point to very dense area where users are packed very closely, like in stadium and your downtown area where the difference between two users are very close. And but there are challenges, right? It's not easy to implement things in 5G in new RAT. So multiple antenna arrays are required for spherical coverage, because now what will happen that when you move to high frequency band, your beams become very narrow. So to have a coverage, 3D coverage, a spherical coverage, you need to have multiple antenna arrays, right? All three directions. And integrated IC design and system design becomes very complex, because your transistors or CMOS devices, what we are using, they are meant for frequency in few gigahertz, but now we are operating it at 24 gigahertz and above, and wavelength is millimeter wave, so design will be totally different. And challenge will be discovery and tracking. So mobile devices, if your device is testing, life is easy, but your device starts moving, so how to track? First, how to discover where is your user when it is moving, and then how to track it because it is moving. So this is very, very, very critical. So localization position is very critical in new radio technologies. So best part is that we have massive MIMO to help you out. You see that we have antennas in both horizontal, vertical and space directions. So it achieves high throughput and it takes care. So what it happens that reduced transmit power. One of the constraint of 5G is that transmit power should be reduced and fast fading prevented, because if you are moving at high speed, there will be fast fading. Power efficiency should be good, low power consumption. So these all are achieved through this massive MIMO using these four techniques, and you should be aware of these all four techniques. One is spatial multiplexing. We are getting the multiplexing gain in spatial domain. Then we are talking about spatial diversity gain. What we got in 4G is in one direction, but now we'll get a spatial way. Array gain, because we have using multiple arrays for physical coverage, so we need array gain. Then we have to go for multi-user diversity, right? This is all we require in massive MIMO. But there are challenges. I told you that things become very easy. No, it is not so easy. We have everything. We have challenges. Definitely, it has a capability to improve radiated energy efficiency by 100 times, and the capacity is overall increased by 10 times, right? This is the advantage of massive MIMO. These are the advantages I'm discussing. And it can put together with the help of low power and less costly components, because your antenna size is very small and it needs less power to radiate, because more if you move in higher frequency band, power transmission requirement will be less. And MAC layer, this multiple access layer, becomes very simple, and it strengths. So it gives you the strengths equally against band-made jammers as well as interference. So these are multiple advantages of massive MIMO, but there are challenges. And as an engineer, you have to more think about challenges, right? What is done, that is done. So challenge is that so a lot of baseband processing required, huge amount of antenna uses, right? Because multiple antennas are there. Hardware impairments. So 256 antennas, 264 antennas, right? Phase recovery, so multiple phase arrays, fast fading thermal noise are averaged out. Antenna demands phase synchronization, and they suffer from pilot contamination from other cells. So they are multiple antennas. They can easily pick up signal from any other antenna nearby. But advantage is that if we combine millimeter wave with massive MIMO, they complement each other. What I mean to say that complement each other is that at millimeter wave, if you see this millimeter wave, there are a lot of attenuation. Water droplets can attenuate to a signal, oxygen layer can attenuate signal. There are a lot of losses. How these losses can be compensated? By using this massive MIMO, because massive MIMO path loss can be mitigated by using high gain antennas, because at millimeter wave, using massive MIMO, your antennas will be highly directional and gain will be quite high. So they complement each other, and then we can have very successful and reliable transmission at millimeter wave. Or in other words, if you see the frequency band here, we have a band around 24 to 28 gigahertz, which right now we are targeting. You see that, but the problem with this 24 to 28 gigahertz that it is attenuated by red droplets, right? Rain and moisture droplets. It is highly attenuated, right? So last slide. This is all about vision of 5G. Different companies, they have different visions like Ericsson, Qualcomm, Docomo, Nokia Solutions, 5GPP, then 5G now. These are the main thing. But I will try to mention here a very, uh, vision of Nokia Solutions, right? What Nokia says that 5G is all about heterogeneous networks, augmented reality, and tactile internet. So, because other things already we have achieved in 4G, but this augmented reality and tactile internet is something which will be very, very new to us, very new user experience in 5G, right? Thank you. And I'm now open to any question you have. Please. Any question? Ravi. Yeah, I have got. Yeah, 3:30 is concluded, and